Hi, I'm Deepali Jain. I work in robotics at Google. Let me present our paper From Pixels to Legs, Hierarchical Learning of Quadruped Locomotion in collaboration with my colleagues Atil Iscen and Caluwaerts. In this paper, we tackle the problem of visual navigation for legged robots through hierarchical reinforcement learning. The main contribution of this paper is that our hierarchical solution implicitly learns a complete pipeline from pixels to motor commands for quadruped legged locomotion without the need to design or learn low-level behaviors. This is our problem setup. We design and train a hierarchical policy to control the Like-A-Go robot to perform navigation in various 2D environments. The policy observes images from a camera mounted on the robot and observations from other onboard sensors and produces motor commands. Our hierarchical policy is split into two levels, high level and low level. Here is a more detailed schematic of our policy architecture. The high level is a convolutional neural network, which observes the depth camera observations and issues latent commands to control the low level. It also outputs the duration until the next high-level execution. This reduces the high-level control frequency and introduces temporal abstraction in the policy. In some cases, task-specific inputs, such as the robot position and orientation, can be fed into the high level. The low level is a linear neural network that controls a cyclic leg trajectory generator. It observes the latent commands from the high level, the trajectory generator state, and other onboard sensor observations such as IMU and motor positions. It controls the trajectory generators and outputs motor commands. Due to temporally abstracted nature of the policy, the high level runs at a low frequency while the low level runs every control time step. This significantly improves the training and inference efficiency of the policy. To train our hierarchical policy, we use an evolutionary algorithm called augmented random search to maximize the reinforcement learning episode return. The algorithm proceeds by iteratively estimating gradient of return with respect to policy parameters and performing gradient ascent. We designed 3 navigation environments for our experiments. First is a task to cross a randomized curved cliff. In the second task, the robot starts in the random orientation from the middle of a maze filled with obstacles. The task is to move away from the origin. In the last task, there is a goal located randomly at one of the 4 corners of the maze, and the robot has to find it. In all 3 cases, the robot observes the environment through a first-person camera view. In the goal-finding task, the robot also gets the relative position and orientation of the goal. Here are some video demonstration of our learned policy navigating these environments. In the goal-finding task, the robot efficiently turns in place to face the goal using dynamic leg movements, which are difficult to hand design and tune. Here are the trajectories of the trained robot in simulation for the 3 environments. The dot markers along the trajectories show the points at which the high level becomes active and computes the next latent command and duration. We compare the learning curves for our hierarchical policies with non-hierarchical convolutional neural network policies on these 3 environments. We see that in all 3 cases, our method largely outperforms the baseline. A trained low level can also be transferred to new tasks in unseen environments. This allows sharing of primitive skills across problems. We reused learned low-level skills from goal-finding tasks for training new policies in the maze traversal and curved cliff tasks. In both of these cases, we observed that this improves the learning efficiency. To better understand the behavior of the learned policy, we visualize a 2D latent command space for the goal-finding task. For a learned hierarchical policy, we evaluated the low level with artificial latent command inputs taken from a uniform grid over the whole command space. These behaviors are shown on the right in the form of robot trajectories running for 1 second in the XY coordinate plane. On the left, we show the latent command space points for which these behaviors emerged in corresponding colors. For each point, we generate a vector summarizing the low-level trajectory. Vector direction shows the movement direction of the whole low-level trajectory, and the length is proportional to the distance covered. This visualization shows how the latent space is used to smoothly transition between the robot steering behaviors of various velocities that have emerged automatically. To study the effect of temporal abstraction, we show the inference times for policies with high level running at different frequencies. It is clearly inefficient to run the high level every time step, given that we can achieve optimal return about 100 times faster with the temporally abstracted policies. Finally, we also trained our hierarchical policies in simulated 3D spaces with realistic visuals from the Gibson dataset. Thank you.